Section 3.5, Rate of Change. So let's look at an example and see what they want us to do here. The average attendance at USC home football games increased approximately linearly from 59,000 in 2001 to 91.4 thousand in 2006. Find the average rate of change per year of the attendance. So the key to this is to realize that when they ask us for an average rate of change, they're actually asking us to make a calculation very much like the slope. So we're trying to do change in one thing over the change in another. And we can tell which one goes on the top and which one goes on the bottom by looking at the units. They want the average rate of change per year, so that when it says per year right there, that tells us in the bottom we want the change in year, and then change in attendance would have to be in the top. So when we typically do slope, that would be change in y over change in x. So we want to use this idea of looking at their wording to help us figure out what's the input and what's the output. We know that normally it would be input of x, output of y. So our ordered pairs on this one must be an input of the year, and the output is attendance. So now if we look at what information they gave us, they said it changed from 59,000 in 2001. Now if we go to make an ordered pair out of that, you might be tempted to put 59,000 comma 2001, but notice that the x is the years, so that has to go first. So I would actually write that ordered pair as 2001 comma 59.0, and I do have to remember that's in thousands. That'll come into play as I finish this off, but for now I'll just write the ordered pair. And then we want to do the same thing for the other information they gave us, 91.4 thousand in 2006, and again change in x is on the bottom, so that's going to be the change in year, and year is 2006, and the output there is 91.4 thousand for the attendance. So now that we have this written as two ordered pairs, it should start to feel a lot more like it did back in the previous sections. So we're just going to go ahead and do that change in y over change in x type of calculation, and we usually like to do the ending point minus the beginning, so I'll do 91.4 minus 59.0. Notice that the output, or the second coordinate, is what goes on top, just like when we do x and y. And then since I started with 91.4, I need to start with the x, or input, that went with that, which would be 2006. And then subtract the other x value, 2001. And that's our setup. And when we have messy numbers like this, we're usually just going to go ahead and go to a decimal. And so I'm going to go ahead and round this, and I'm going to use the calculator to figure out what it would be. So just a reminder, we've seen this a few times now, but if you are doing a fraction in the calculator and there's more than one number in the numerator or denominator, you want to put parentheses around the numerator and denominator as they go into the calculator. They're not necessary to write on paper like that, but it's just a good reminder for us. So we go ahead and do that calculation, clear out that old stuff. So open parentheses, 91.4 minus 59.0, close the parentheses, divided by open parentheses 2006 minus 2001, and close those parentheses. And then let's see what we get. 6.48. So I was thinking I was going to round that, so I put the approximately equal, but since it comes out exact, I'll go ahead and try and straighten those out and say it's 6.48. But I think it's important to keep the units on there. 6.48 what? Well, this was 91.4 thousand and 59.0 thousand, so this is still 6.48 thousand. And in the bottom, this would be 5, or sorry, we did the whole thing, so that would be a 1 since we went to a unit ratio. But 1 what? It was this was a year, that was a year, so that would be 1 year. So 6.48 thousand per 1 year. And then even though I put the thousand on there, I really haven't put the units. This was about attendance, so this would be people attending. So I would say the average rate of change is 6.48 thousand. Let's go ahead and just call them fans, I guess. So 1,000 fans per year. And that would be my answer. And so you should notice that as we went through and we did that, that calculation felt an awful lot like just calculating a slope did, with messy numbers, but that's pretty typical once we start moving to real life data. And so this box is just kind of making that statement that a slope and an average rate of change is the same thing. So if two quantities t and p are approximately linearly related, and if p depends on t, then the slope of a reasonable linear model is approximately equal to the average rate of change of p with respect to t. So again, the key thing is saying that that slope is the same thing as that average rate of change, making that equivalent. So when we hear them ask for an average rate of change, we can do the math on that just like we would for any other slope. The key is figuring out which is your input and which is your output, and looking at the initial question to see what it's per. If it's per year, years are on the bottom, that's your input. So let's look at that with another example, see how that goes. So the percentage of firearm applications that were rejected declined approximately linearly from 2.4% in 1999 to 0.9% in 2007. Find the average rate of change per year of this percentage. Notice again that it is per year. So that indicates that we're going to be doing change in something over change in years. And what's the something? It's the percentage of firearm sales, so I'll just say change in percentage. But this does indicate to me that the years are my input and the percentage is the output, because again, what we're used to for slope is change in y over change in x. So whatever is in the denominator, that's our input, and the numerator is our output. So if you go back, we look at this, we have 2.4% in 1999, that's an ordered pair. Put the year first, put the percentage second. And then what's our other information? It was 0.9% in 2007. So we have 2007, comma 0.9%. They're asking for an average rate of change, but we said right above, if they ask us for that, we're just going to do a slope calculation. So in fact, I'll go ahead and even label that as M, just to be kind of in that normal setting that we've been doing. And I'm going to start off with my ending point and then use the beginning point as my subtractor. So doing the change in output on top, 0.9 minus 2.4 over 2007 minus 1999. And again, I'm going to go ahead and do that on the calculator, so I'll put parentheses around the top and the bottom. And this time I'll hold off on the symbol to see if I have to round it or not. But let's go ahead and do the math just like we did last time. 0.9 minus 2.4 over 2007 minus 1999, and parentheses around numerator and denominator. So this comes out exact, so I'll put that exact figure, negative 0.1875. And then we'd want to interpret that. So what were the units? On top we have percent, and on the bottom we have the years. So I would say that the rate of change is negative 0.1875%. And what are we talking about here? The percentage of firearm applications that were rejected. So they're declining at 0.185% per year. And we'll just do that with a slash. So that would be the average rate of change. And then I guess one other thing that we could look at here, they do say they declined. So I do want to point out that when they say it's going down or it's declining, you should expect that you would get a negative slope, and notice that we are getting that. And I would include that in the answer too, because they did ask to find the average rate of change, and so I would put the sign on that as well to indicate that it is a decrease or that things are declining as they mentioned. Alright, let's go ahead and look at one last example on this page and see what variation that brings for us. So the percentage of all U.S. workers who are in a union was 12.1% in 2007, and it has decreased by about 0.29 percentage points per year. Let P be the percentage of workers who are in a union at T years since 2007. Find the slope of the linear model that describes this situation, and what does it mean in this situation. So when I hear find the slope, at first I think, well, we'd have to do some work like this. But remember, slope is the average rate of change, and they're saying that essentially they're giving us that right here. They're saying it has decreased by 0.29 percentage points per year. Notice they talk about percentage points per year. That was the same sort of wording that we saw when they asked us for the rate of change, and now they're using those same units and they're giving us the number. So that number is going to be our slope. So our slope is 0.29% per year. And then one missing piece on that, though, is this increasing or decreasing. They said right here it's decreasing, so that tells us that our slope is a negative number. So I would say that the slope, or m, is equal to negative 0.29, and I would go ahead and just put that in terms of the answer for what's the slope. But then when we go to describe what it means in this situation, or what does it mean in this situation right here, now I want to put units on that. So I would say, okay, so it's negative 0.29, but what did they say the units were? Percentage points, so percent, and then per year. So I'll just put the year on the bottom, and when there's no number, it's good to put a 1 to help you interpret it. And then I find that when I'm interpreting slope, if I go from the bottom up, that always gives me the smoothest interpretation. So I would say for each additional year that goes by, the percentage of U.S. workers who are in a union decreases by 0.29%. So let's go ahead and try and write that out. For each additional year that goes by, reading the bottom, and then switching up to the top, what's happening to the percentage of workers who are in a union? It's going down by 0.29%. So we just read that through one more time, make a couple notes about that. So for each additional year that goes by, the percentage of all U.S. workers in a union decreases by 0.29%. And one thing I want to point out is that even though the slope was negative, I didn't put a negative here. When they asked me to explain what the slope means, I'm going to explain what that negative means, and a negative means that things are decreasing. So I didn't use a negative in the sentence, but I translated that negative into the word decreases by. Alright, let's go ahead and look at this last piece. Find the p-intercept of the model. What does it mean in this situation? So p was the percentage, so that's our output. So the p-intercept would be a 0, some percent that we would want to try and figure out. And the 0 would mean that there was a 0 for our input. So what was our input variable? Let's see, we're saying p is the output, so that means that t is the input. And t is the years since 2007. So if t is 0, that means we're in 2007. And in 2007, the percentage was 12.1%. So I would say that 0, which represents that 2007, would have what percentage with it? 12.1% union membership. I guess we could just put 0, 12.1, but when it says what does it mean, I want to think about those units, and that's when I started thinking, okay, this is 0 years and 12.1%. But I don't want to say 0 years since 2007. I would just say in 2007. And then I would express this part, that the percentage of all U.S. workers in a union was 12.1%. Or I guess we could say that a little bit smoother, maybe in 2007, 12.1% of all U.S. workers were in a union. So when you're trying to interpret these things, whether it be a slope or a y-intercept, just go ahead and get the initial number, the slope. The y-intercept is an ordered pair. But before you try and put it into words, always make sure you put the units on, and that should help that process go smoother in either case. Okay, continuing on with that example, in part C they want us to find an equation of the model. And so the key thing to remember here is that we're going to do a linear equation, and those have the form y equals mx plus b, where m is the slope and b is the y-coordinate of the y-intercept. So if you look back at the work we've done so far, we've gotten the slope and we know the y-coordinate, the y-intercept, so we can just plug those in. So I can say y equals, and then instead of mx, I'll put negative 0.29x, and then instead of the plus b, I'll put the y-coordinate of the y-intercept, which is that 12 plus 1, or 12.1, so I'll put plus 12.1 right there. And that would be the equation of the model. The only problem right there is that I used x and y, and I would kind of recommend that you do that too, because we're kind of used to using those variables. And then translate it. What we still need to do is translate it over into the proper variables. Our output variable is supposed to be p, and our input variable is supposed to be t. So I just need to swap those out. So now I'm going to say p equals the slope, negative 0.29, times the input variable, which would be t, and then plus that 12.1. So I went ahead and got the equation by just plugging in the slope and the y-coordinate of the y-intercept. And feel free to do that with x and y if you're more comfortable with that. If you feel okay with it, go ahead and go straight to the variables you need, which are an input of t and p. But for a lot of people, it's easier to do it with x and y first and then just switch it over to the variables you want after. Now, once we get that equation, this prediction they're asking us to make should be somewhat of an easy job. They want us to predict the percentage of workers who will be in a union in 2014, and so what we want to do is just use our equation to do the best we can with that. So in 2014 we have to figure out what would t be, and t is the number of years since 2007. So I would just take 2014, I would subtract away the 2007, and I get t equals 7 for that. So now to make my prediction, I just want to plug that into the equation. So if I do that, I get p equals negative 0.29 times our input variable, which we just figured out was 7, and then add that 12.1. And that's a little bit messy, so I'll go ahead and do that on the calculator. So we have negative 0.29 times 7 plus 12.1, and we get 10.07. And we just have to think back about what were we doing to figure out what the units should be. So p is our output variable, and that was percentage, so this should be 10.07%. And I think it would be good to say what that means too. So 10.07% of U.S. workers are in a union. And of course that would be in 2014. So there's our answer, and there's a quick interpretation of it, which just matches up with what they asked us. Okay, let's have a look at this box. Constant rate of change. Suppose that a quantity p depends on a quantity t, then if there's a linear relationship between t and p, then the rate of change of p with respect to t is a constant, and if the rate of change of p with respect to t is a constant, then there's a linear relationship between them. So really what they're just trying to summarize there is this idea of a constant rate of change and a line go hand in hand. If it's a line, it's going to be a constant rate of change. If it's a constant rate of change, it's going to be a line. Alright, let's go ahead and take a look at another example. For the spring semester 2009, California residents paid an enrollment fee of $20 per unit at Kenyatta College. Students were also required to pay a $16 health fee each semester. Let C be the total cost plus health fees for U units of classes. Find the slope of the linear model that describes the situation, and what does it mean in this situation. Alright, so when you're looking for the slope, you could look for two-ordered pairs, or, like they said in the box here, if it's a linear relationship, you could look for the rate of change and get that constant rate of change to be your slope. And so if you're looking for a rate of change, you'd want to look for the word per, and I see that right here, that the enrollment fee is $20 per unit. So notice that we have units of cost over units of how many units you're taking. And so that's going to be our slope. So m is equal to 20, and if we wanted to think of that as a fraction, we could say 20 over 1. And then I think it would be a good idea to put the units on there so that we could interpret it as they wish for us to do. And that would be on the top $20, and on the bottom that would be 1 unit. And then I want to go ahead and interpret that. What does it mean in terms of this situation? and I would always do that from bottom up. So I would say for each additional unit that a student takes, their cost is going to increase by $20. So for every additional unit the student takes, or a student takes, their cost will increase by $20. I didn't mention that right here, but of course it is an increase, right? You expect that if you take more units, you're going to pay more money, and so that went hand in hand with having a positive slope right there. Okay, so now they want us to find an equation of the model, and so if we have a constant rate of change, that would be a linear model. So I'd be thinking I want something along the lines of y equals mx plus b. If we look at our slope, that gives us a clue of what our variables are going to be here. In the bottom we have units, and in the top we have dollars, which is the cost. So the number of units is our input, and the cost is our output. So the output is C, the cost, and the input variable is going to be U. And so our task here, if we want to come up with that equation, is to figure out what is the m and the b that needs to be plugged in there. Well, we already know that m is 20 from up here, so we just have to find the b. And when you're looking for the b, that you'd think about the y-intercept, 0 something, right? What is that? Well, the input there is units, so that would be if you took 0 units, how much would you pay? Well, of course, if you didn't take any units, you shouldn't pay anything. You're not going to that school, right? But another way that you could think of it, besides like what if you weren't going there, is before you even start paying for your units, is there any other cost that you have to pay regardless of how many units you're taking? And that would be what we call a fixed cost, something that doesn't have that per. It doesn't matter how many units you're taking, you're just going to pay that amount. Well, there's only one other cost listed, and that's this $16 health fee right here. And that's not per unit, that's just each semester. So for each semester, that's a fixed cost. You have to pay that whether you take a 1-unit PE class or a 12-unit full load, or like an 18-unit hyperload. It doesn't matter. It's $16. So that sounds to me like that's going to be that B right there, 0.16. So now we know that our B is 16 and our M is 20, so we can write our equation using the variables of this problem and say that C equals the slope, which is 20, times the number of units that you're going to take, plus the fixed cost, or the y-coordinate of the y-intercept, which would be that $16. So there's our equation. And then they're also asking us to perform a unit analysis on this equation, and that's something that we can do kind of quickly. It's just kind of a quick check to think about, did I do this equation right? And one way that you can kind of confirm that somewhat is to see if you have the same units on both sides. So on the left side we have cost. So what would the units be on cost? So what's our left side? The left side is cost, the units would be dollars. Okay, so that's simple. How about the right hand side? We're hoping that we're going to get the same thing there. When you get the two sides to have the same units, that is a good sign that things are going right. If the units don't agree, the equation cannot be right. So let's think about what the units would be. So the 20 was the slope, so that actually had some units on it. That would be $20 per unit. And then we're multiplying that by U, which is the number of units. And then we're adding 16, but 16 what? It was a fixed cost, remember, of a health fee of $16. And the amount isn't important. If you want, you could plug in some number of units like 5 or 6 or something just to see what happens. But the key thing that happens is the units cancel out here, and we have dollars plus dollars. So what are the units on the right-hand side? They're dollars. So what's kind of the conclusion of my unit analysis? The units on the left and the right are both dollars. That's the same. That's a good sign. So I'm just going to go ahead and say check there. So this is something that is, I would say in my opinion, that's kind of an optional step. You're just checking your work to try and confirm that you have a good sign that things have gone right on the units. If that step does not work, you have got something going wrong in your equation. Alright, let's go ahead and finish this off. What was the total one semester cost of tuition plus fee if you took 15 units of classes. So they're asking us about 15 units of classes, so they're saying that U is equal to 15. Excuse me. And so they just want to know the cost. We have an equation for that, so we're going to plug in. The cost is going to be 20 times 15 plus 16. That 20 times 15 is 300 plus 16, that's 316. Well, 316 what? Well, it's cost, and our units on cost were dollars, so that should be $316 as our cost for taking 15 units at Kenyatta College in the spring of 2009. Alright, on this page we're going to go ahead and look at another example, but this one involves data, so let's go ahead and see how this one goes. In an attempt to raise the low graduation rates of college football and basketball players, Division I institutions require prospective athletes to meet new GPA standards to play as freshmen, and enrolled athletes must meet these new standards to keep playing. See the table below. So they list a SAT score, and we have 6 of those, 620, 700, 780, 860, 940, and 1010, and then a core GPA. And so what they're saying here is that if your SAT score is higher, you would be able to play in college athletics even if you had a GPA that was low. But if you get a low SAT score, then in order to still play college athletics, you'd have to make up for that by having a high GPA. And they're claiming that a good model for that would be G equals negative 0.00254 times S plus 4.58, where G is the core GPA, so we'll go ahead and label that up here as a G. And then the SAT score would be an S. Let me go ahead and write that on the side, maybe a little bit more clear. So let's go ahead and have a look at the data and the equation and see if that does in fact look like it's a good model. So they want us to use a graphing calculator to draw a scattergram and the model in the same viewing window, and then does the line come close to the data points. So let's go ahead and do that process. I'll bring the calculator in here. So the first part would be to enter the data. So we're going to press the stat key. Go ahead and raise that up a little bit. So I'm going to press the stat key and go into edit. I have some old data here from another problem, so I'll use my arrows to highlight the list name. Clear and down arrow will erase that. Again, highlight the list name, clear and down arrow will get rid of those. So I'm going to go ahead and put these input SAT scores in. And then I'm going to use the arrows to move over to L2, and I'm going to put in the core GPAs that go with those. And then I want to plot that and see if it looks linear, and then I want to plot their model in there and see if it looks like it's a good fit. So when I'm going to plot data, the first thing I want to do is think about setting up the window. So let me go ahead and hit the window key to do that. My input variable are these values of S, and they go from 620 to 1010. So first I might think about like what kind of scale do I want there. Maybe I would number in 50s. Not terribly important, but I'll go ahead and pick that. And then I want to pick something that's like a multiple of that scale and a little below my smallest value. So I'm going to start out at 600, a little bit smaller than 620 and a multiple of 50. And then for my max, I need to make it up to 1010, but I want to end on a multiple of my scale. So I'm going to go with 1050 there. And then I'm going to go over and think about the GPA in the same way. So GPA only goes from 2.0 to 3.0, so maybe a good scale would be to go in tenths. And then for the minimum, I want to go a little bit below that 2.0, so I'll go with 1.9. Whoops, 1.9. And then for the max, I want to go a little bit above their max of 3.0, so I'll put 3.1. And we'll go ahead and take a look at that. So we want to see the data plot, so we probably have the plot set up, but I'm just going to make sure, and you could do this too. Above your y equals, it says stat plot, so second stat plot. And I'm just going to verify that I have all the right conditions set. For plot 1, it's on. That's good. It's a scatter plot, and the variables are in L1 and L2, and it's going to graph with squares. So that sounds perfect. So if I hit graph, I should see that. So there's my data, and that looks nice and linear. A very good linear pattern to that, so it makes sense that we would model that with a line. But now we want to see, is the model that they gave us actually a good one? So if I hit the y equals key, that's going to allow me, I can see by the way that the plot 1 is on, but I'm also going to be allowed to enter in an equation. So I want to enter in their equation, and instead of g equals, we have y1 equals, and then negative 0.00254 times, it's supposed to be s, but when you're using the graphing calculator you will always use the x as your input variable, and then plus 4.58. So there's our equation. Let me just go ahead and move this back over here again so we can still see the data. And I'm going to hit graph again, and we should see that same plot and this line drawn in, and hopefully it's a good fit. That looks really nice, right? It seems to have kind of nicked every one of those squares. If we were able to zoom in, it's probably not hitting them perfectly, but it certainly seems like a reasonable model. And that was the question they asked us. So let's answer that one. So use the graphing calculator to draw a scattergram. Check. And the model, which is the line. Check. We did that too. And does the line come close to the data points? Yes. Extremely close, I think we could say. Alright, so now, if an athlete's SAT score is 400 points, which is the lowest you can possibly get on the SAT, estimate the student's qualifying core GPA. So when you take a SAT test, they give you 200 points right away. And back when this problem was written, there were only 2 tests, the math and the English test. And so there was 400 points was the lowest you could get. Nowadays there's 3 tests, so that's probably 600 for the lowest. But this table was all set up back in, I think, 2007. So we'll just go ahead and go with those numbers. And so how are we going to do that? How are we going to figure out like what GPA would you need if you got the lowest possible SAT score? Well, we will use our equation, but we only want to use the equation if it's a good model. But what did we see in part A? And when we looked at the graphing calculator, it seems like a really good model. Like that equation has a line that is hitting, if either coming really close to these points, maybe even hitting them. So using that model to make predictions, I think, makes sense. So when they give us the 400, they're giving us a value of s. So s is 400. So g is equal to negative 0.00254 times, instead of s, we would put 400, and then plus 4.58. You could do the pieces by hand, but it is kind of messy, so I think I'm going to go ahead and switch over to the calculator. I'll hit second and quit to get back to the normal screen. And negative 0.00254 times 400 plus 4.58. So I get 3.564. And I think we want to put units on there too. So I guess that would probably be, actually I think about GPA, I don't even know what the units are. We usually don't say any units, but because of that, to make it clear what it is, I think we should say that it's the GPA. So student would need a core GPA of 3.564. So if you're going to score that low on the SAT in order to continue to play college sports, you need a GPA of 3.564, which is kind of right in between an A and a B, so kind of, like 50-50 A's and B's pretty much would get you right around there. Alright, so now they're telling us that the actual qualifying core GPA is 3.55, and they want us to compute the error of the estimate. So we might remember back from chapter 1 that if you're going to do that, the error, we'll use a little e for that, is the actual value minus the estimate. And so they're telling us what you really need is a 3.55, so that would be the actual. But when we used our equation, what we came up with was 3.564, and I'll just do this on the side, but if you subtract those two numbers, you get negative 0.014. So that's the size of our error, and I guess the thing I would point out there is that seems like a very small error to me. I could imagine that if I was advising the student and I told them I think you're going to need a 3.564 as your GPA, and they found out they actually needed a 3.55, they wouldn't be too upset with me because I gave them a number that was very near what the reality is. And the reason we're getting such a good close estimate from our model is because the data was very linear and the model did a good job of coming close to all those points. So even the points that weren't in the table, we should still be getting close to them. Alright, one final question on this one. What is the g-intercept and what does it mean in this situation? So the g-intercept would be a 0, b. G is our output variable, so it would look like this. And we could plug that into the equation, or we could just look at the equation, in fact, and say, look, the g-intercept always has this constant term as its second or y coordinate, and so that's going to be a 4.58 for our b. So the g-intercept would be 0, 4.58. When you go to think about what it means, I always like to put units on it. So the 0 would be the SAT score. So 0 on the SAT, and then this would be the output would be a GPA. So you need a 4.58 GPA. So one temptation would be to say if you took the SAT test and you scored a 0 on it, then you'd need a GPA of 4.58 to play college athletics. And a couple things to say. Generally, 4.58 GPA is not possible. Perhaps with AP courses or something it could be, but actually it all turns out to be irrelevant because a 0 on the SAT test is not possible. If we look back up here at Part B, it says the lowest possible score you could get was a 400. So a 0 is not going to happen. So what does this mean in the situation? I could start to interpret it this way, but I think the better answer is it doesn't mean anything. A 0 on the SAT is not possible. And that means that the g-intercept is irrelevant. Alright, on page 19 we're going to look at one last property and one last example. So the slope addition property says for a linear equation of the form y equals mx plus b, if the value of x increases by 1, then the value of y changes by the slope. In other words, if an input increases by 1, the output changes by whatever the slope is. Now this sounds familiar to me because this is the way I always interpret slope. Earlier in these notes I said things like, if the number of units you're taking increases by 1, then the cost of going to Kenyatta College will increase by $20, which was the slope. So I use this idea of the input goes up by 1, the output changes by the slope every time I go to interpret. But this next example shows us another way we could use it. They want us to find an equation of the line for each of the points that are given below. And if we look at these points, they're increasing by 1, 0, 1, 2, 3, 4, and those are our inputs. So because the x is increasing by 1, whatever the y increase is, that's going to be the slope, because the y is the output, and they're saying that change is the slope. Now, if you're going to use this idea, you got to be very careful. I'm saying here that this difference will be the slope. So what's happening is these go up by 1, 22, 19, 16, 13, 15. Looks to me like the pattern is that these are decreasing by 3. So for set 1, I see that decrease every time of 3, so I want to say that the slope is negative 3. And I can only do that if these are increasing by 1. So this part is really important. You can't just look at ordered pairs and say however the y is changing, that's my slope. You can only do that if the x's are going up by 1. If they're not, you need to just take these ordered pairs and compute slope using change in y over change in x like we did in previous sections. But when you have it, you should take advantage of it. So if m is negative 3, we're halfway to getting our equation. We just need to figure out what the b is. And we know b comes from the y-intercept. Well, there's a 0 input with a 22 output, so that looks like b is 22. Because whatever y coordinate goes with an input of 0, that's your y-intercept. And so if you've got m and you've got b, then you're pretty much there on the equation. We just need to write it down. Y equals mx plus b, so y equals negative 3x plus 22. So there's my equation for set 1. And now let's try the same thing for set 2, if we can. And I say if we can because it does depend on what that spacing is. But when you look at this chart, 0, 1, 2, 3, 4. So these are going up by 1 just like last time. So we can use that same idea. If these are going up by 1, then whatever the y is going up or down by, that's going to be our slope. And I look at those y values, 3, 7, 11, 15, 19. It looks like they're going up by 4 each time. So that means m is equal to 4. And then for the y-intercept, here's our 0 input. That has an output of 3. So that means b is 3. Put those two facts together and we have y equals mx, so 4x, plus b, so plus 3. And there's my equation for set 2. So that's pretty awesome, fast way to get your equation. But to do it, you have to have this increase by 1 on your x values. If you don't have that, you need to just pick two of these and do change in y over change in x and calculate your slope like we did in previous sections. Alright, that wraps up chapter 3.